Hey, welcome back. Let's talk about these parts. I have to make 25 of these out of PEEK, which is a high-end plastic, and I just want to take you along the journey how to make these. Let's look at them in CAD and then see how we machine them. Here we can see the part in CAD, both sides of it. I got a 2D hand sketch supplied by the customer and the 3D model is by myself. You can see the counter bore in here. There's a 5mm diameter here. It's counter board, and then it's an M3 thread all the way through. This large diameter is 80mm and overall height from here to here is 40mm. So it's not a crazy complicated part, but some of the features are a little bit tricky. The relatively small distance between the domes and the ID of the part here are a bit tricky because you need a relatively small tool with a reasonable long reach, and also those very small, very high domes on this side of the part are a little bit tricky, and you have to do them in the right order of operations. And then here in the center it's just an M5 thread. So that's here in CAD. And I also can show you the clamping fixture to machine the second side. The green thing here is the clamping fixture, and in those 4 positions in the corner with the countersink here, that's where the screws go, the expander screws. The screws go in and deflect this thin-walled section here against the part and clamp it. I can show you a through cut through the part. This large flat rests here on the fixture, so this thin bottom here is only, I think it's 3mm thick. It will not vibrate, and this OD here is captured by the ID of the fixture, and those domes orient in those 4 cutouts. So it's slightly over constrained, but it works quite well. So let's go into CAM. This is Bobcat version 32. That's what I'm using. The translucent here, that's my stock. I turned it on the lathe to a diameter of 80mm and a height of 40mm. Then I went to the mill and cut the domes. Adaptive strategy here. This is all roughing with a 6mm end mill. As you can see, the tool cannot reach around those 4 domes. Just cutting a radius here. The next tool is, this is a 2.4mm end mill that's relieved 12mm to cut those 4 domes and the ID of the part to a finished dimension. And also finish the bottom with a parallel toolpath. No, not parallel. It's a spiral toolpath. That leaves a nice finish on the bottom here. And we helical mill those 4 counter bores. Just helical down to final depth. No finishing. Helical mill the central bore. That's a little bit odd. I'm using an engraving tool path to finish this rim around here to final height. I can show you the tool path. It basically cuts on center line here and walks the way around like this, retracts, goes down, and this side too. It's not the ideal toolpath. I was a little bit lazy when I programmed that. And I have a chamfer mill, chamfering the ID and OD of those domes. Chamfer mill to chamfer the rim around the part. And finally a drilling operation. Where is it? There we are. There is backplot. I'm still reasonably new to the software, so excuse me if I have to look for buttons sometimes. So this is a full retract drill cycle because I want to get the chips out there. And it goes like this all the way around. So that's the first side. We can let's undo post-process. We can run a simulation on the part 2. This is a 6mm end mill running at 1200 millimeters per minute and 12,000 RPM. Let's speed this up a little bit. Now it's cutting the pocket. Nice adaptive strategy. And here we are with the 2.4mm end mill. It's cleaning up those domes. Yeah, it's taking a full slotting cut back here, but it wasn't really an issue. Cuts all the way down. The 6mm tool had allowance above the bottom, 0.1mm. So cutting the 4 domes. Cutting the ID of the part. This is going at, I think it's also 1200 RPM, 1200 millimeters per minute, but higher RPM, 16,000 I think. Finishing the bottom, giving it a nice finish. Boring those counterbores, spiral toolpath. Chamfering, doing a nice 0.2mm chamfer on each edge, saves me from doing it by hand, and drilling, drilling all the way through here. So there we go, that's the first side. Flip the part around, take, let's get this one here, post-process, go out of wireframe, and for this side, I started with a chamfer end mill, and I chamfered the ID of this hole and the OD of those 4 posts, or domes, because once those posts are completely cut free, when you chamfer them, you get crazy vibrations. Then we have and I just take a very, very light cut on top of those domes, just to clean them up ever so slightly from any other tool marks. And we have pocket operation, that's quite impressive. That's an adaptive strategy to cut all the material away. And one final operation to clean up the floor of this part. No roughing finishing. I'm already cutting it to final dimension, because otherwise, if you came back to the finish posts here and tried to do a finishing cut on their outside, all hell would break loose. They would vibrate all over the place, so that's no good. You could do it in layers, rough one layer and finish one layer, and then pattern it down, but this worked quite well that way. So simulate the second side. Okay, hide the tool paths. Slow it down. Here it starts by doing those chamfers. Doing a cleanup on the top of those domes, and now it's just adaptive, clearing away all the material. I went for adaptive. Normally I don't run adaptive in plastic, but in this case I didn't want any full engagement of the cutter because with that much stick out on this tool and my low rigidity machine, that tended to chatter quite a bit. So went adaptive. Takes longer that way, but the machine runs unattended once the 6mm tool is in anyway. So stepping down, cleaning up the bottom, there we go. And you already have your small chamfers on those posts. These are out of plastic, as you can hear. This is PEEK, which is a very, very expensive high-end plastic. It's very resistant against chemicals and heat, and very hard and almost brittle, but it machines very nicely. It gives very crisp contours, doesn't leave much burr, basically no burr at all. I can't tell what these parts are for, but it will be interesting to make these. A lot of CNC work, of course. So they start out as this large chunk of PEK, which I cut on the chop saw. Then I turn them on the lathe, then I go to the mill and cut all the features. And last thing that we have to do is to cut tap a few threads in here. 4 M3 threads and 1 M5 thread here in the center. Okay, that's the overall setup on the CNC router. I have a vise back here. This is used to cut the first side. These are the blanks as they come off the lathe. And I cut this internal shape here first. I have a bearing race of a ball bearing in here as a parallel. Part drops on here, goes against the stop, and then I indicate it in. This needs to be reasonably precise because the OD here is already machined to final diameter on the lathe. Once this internal contour is cut, it goes onto this fixture here. These 4 posts register in these cutouts here, and the OD of the part registers, of course, in this large pocket here. It goes on like this. So that's how the part goes down in the fixture, and to be clamped I have 4 screws in the corners. These are countersunk screws, and I have a flexure slot cut in here with an end mill, and once you bottom out the screw against the taper of the head, this section here deforms against the part and clamps it. And that's a very, very rigid and very secure way to holding this part without distorting it. I could hold it in a 3-jaw chuck or a self-jaw chuck, but then I wouldn't have the orientation from those pins here. The orientation I get from these cutouts, and the clamping is with these 4 screws. So next day, and I'm just about to start to cut another one of these parts. So turn the machine on. Now we need to run its reference procedure so the machine knows where it is. It will move all the access to their homing switch and set the machine coordinate system in the controller to 0 for each position. Okay, machine is referenced. I jogged over roughly above the part. It's held securely in the vise. And now we need to center on the part. Okay, now I'm using an indicator in the spindle. To center XY on the part. That means you just jog the X and Y axis until the indicator does show minimal movement when you spin it 360 around the part. Now we switch to our first tool, which will be a 6mm 4-flute carbide end mill that's coated. The PEEK is not glass fiber filled, but still it's quite bad for tooling. Uncoated carbide tooling wears down quite fast. Titanium, aluminum nitride coated tools last quite a bit longer. Even better would be DLC coated or diamond coated, but those are crazy expensive. Okay, in order to let the machine know that we have tool 1 in the spindle, we want an M06 in the MDI. M106 is the command for tool change, and we need a T1. That's our tool 1. And we want the controller to load the length offset of the tool out of the tool table. That's a G43. And when you look over here on the C, on the DRO of the controller, this is the C coordinate. When I hit enter, this will change, because then the machine will know that the tool has a different length, and hence the position relative speaking changes without even moving the axis. There we go. It loaded already the C axis, and it asks me, please load tool 1, which I already did, so I can confirm that. To touch off on a part, I'm using a gauge block, 3mm gauge block. I'm jogging down, then I change to the electronic hand wheel, which allows me very fine control. I jog down a little bit past the height of the gauge block, push the gauge block very lightly against the tool, so light I do not damage it. Then I just jog up until the gauge block fits barely under the tool, like this. Then I can come back here in the controller, hit C, it's a G92 offset, hit 3. 3 is the thickness of the gauge block, hit enter, and now C shows 3. So now we're good to go. This is how the parts come off the mill when the first side is done. All the features, internal features milled, except for the M3 threads that go all the way through. These posts are relieved to this depth with a diameter of 5 millimeter, and the rest is an M3 thread. Whether a thread with that much engagement in PEEK is needed or not, let's not debate that. I have the policy on customer parts. If I can create a feature, even if it's questionable, without much extra effort, I will just do it. Except when it's an engineering or a machining problem. But in this case it doesn't hurt. It's just a little bit annoying. So I considered thread milling them, but I didn't want to relieve my only M3 thread mill for almost 28 millimeters of thread depth. So I ordered a new M3 tab from Göring, silver soldered it into an extension so I get a little bit more room to work with, and I turned this bushing here out of steel, which slips precisely over those domes like this, and has this bored to the diameter, to the shank diameter of the tab. The way this works, it's very primitive, but very accurate actually. A little bit of alcohol for cooling. Get the bushing on. Bottom it out. Reverse it. Very precise way of tapping these holes very, very fast. The nice thing about the PEK is its high melting temperature, so I can get away with running the tap at 1000 RPM in and out without melting the plastic. Yeah, I could use the clutch of the drill, but I just prefer to bottom it out and have it slip in my hand. The part slip a little bit. And this is so fast, I don't even consider doing it another way. Yes, it's hands-on time, but only a few seconds per part. I already knew that I'm going to do the threads by hand when I quoted these parts, so that's not a problem. There we go. Clean it out. Blow off the Axis IPA. Give it a number. This is just for me to keep track of the parts. I cut the ID of the fixture a little bit larger so the parts can go in easier, like this. Precision is still given because those cutouts in here intersect precisely with these 4 posts, and this gives XY location even if this diameter is slightly larger. If this larger diameter is very tight, this whole fixture is crazy over-constrained. It still is over-constrained with the 4 posts, but not to a degree where it's a problem. So part goes in, then we tighten down the 4 corner screws. Like this. There we go. Give it a slight hit so it's down on the floor of the fixture for sure. Okay, it did all the chamfering, and now we switch to a 6mm 4 flute bull nose. Bull nose means it's a straight end mill, flat end mill with a corner radius. In this case, 0.5mm corner radius. And this tool has proven to be very good in PEK. It's actually a tool for milling steel, but the combination of the geometry of the tool and the coating seems to last very long in this material. Okay, there we go. Another one done. Get it out of the fixture. There we go. Off to inspection. So we're over at my surface plate and I have a new tool for inspection. It's a Tremos, the Swiss company, height gauge. Currently it's more set up for scribing parallel lines to the surface plate, but it can also do some basic measurements. It works like a standard height gauge. You can move this up and down via this hand crank. You have a digital readout here that you can zero. You have a fine adjust here, and you have a lock here to lock it in place. You can also flip this lever here on the back side, and then you can traverse it quickly, and it's up and down the same force. There is this hardened steel column here is hollow, and it has a counterweight on the inside, which holds this head here in balance. It's almost, can move it with a small finger. You can still use the hand crank to move it, or you can just traverse it by moving it by hand. And this is what you use to move it. You have also this knurled ring here, and this knurled ring moves the head of this this height gauge down a small amount and puts a defined amount of force onto it. So you go close to the surface you want to measure, and then you flick this ring down. Then you have this tip here contacting the surface plate with a constant force. Now you can zero it. You can move it away, and you bring it back in contact, get your constant force, and you go back to zero. This is quite a nifty tool for measuring. So zero, and you can rapid traverse to whatever you want to measure, flip your constant force ring, and you're good to go. So let's check the overall height of this part. It should be 39.9 roughly. 39.94, so 40 micron over. 39.95, 39.9. This is pretty decent for such a thin-walled plastic part. And we can also measure to this height here. We go down close to the surface, flip our ring, 16.36, 16.4, should be 16.4. 16.47, 16.41. There we go. Now we can flip the part around. We take the overall height of the part, 0, and measure from the top of these domes down to the rim of this part. This should be 2 millimeters, 2.01. So that's pretty good. 2.05. 2.04, So that's very close. So that's 3MOS height gauge. You will for sure see this thing more in the future. I have to do a lot of plastic parts in the near future. This is accurate to about 30 microns over a distance of 600 millimeters. This is a 600 millimeter height gauge. So it's not crazy accurate. It's not a TESA height gauge, but it's good. It's quite decent. And just to get an idea how large a 600 millimeter height gauge is. There it goes, there it goes. There's the upper end. It's a little bit larger than I usually would have bought. I would have preferred a 300 millimeter height gauge, but this was so cheap at my used machinery dealer, I couldn't pass it up. And the 600 millimeter is not really a drawback, it's just a little bit heavier and a little bit more mass to move around if you want to slide it on a surface plate. But usually with those, you move the part. I guess that's it for this episode. I have some of these parts left to finish. Hope you enjoyed this mix of CNC, CAM, a little bit of inspection. Thank you all for watching and see you next time.